Apurva, I think you can start.
Shall we start? Hello? Hello?
Hello. Yes. Apurva.
Suparna, you can start, I think.
Okay.
Govinda Bhaiya, please you check in the YouTube that whether it is streaming or not. I am confused. That's why I am asking. Please check.
Millions saw the apple fall, but Newton asked why. Good afternoon to all presents over here in these virtual platforms. My name is Shuparna Das and I welcome you all in the day 4, session 2 of 5 days National Mathematical Webinar organized by Tripura Mathematical Association on the occasion of National Mathematics Day celebration 2021. Now we have the invited talk by Mr. SAGNIK JANA sir from Presidency University. Sir has completed his M.Sc in Mathematics from the Department of Mathematics, Presidency University. So the title of today's talk is Action on Trees. Welcome you, sir, in these virtual platforms. Over to you, sir.
Uh, Hello. Yeah. So, am I audible?
Yes, sir.
So, thank you very much to this web for the webinar and to the uh, all organizers from the TMA. So, I share my screen. Okay. So, so all of you can see my screen. I have shared it.
Yes, sir.
Yes, sir. Yes, sir. Yes, sir.
So my title of the talk is like action on trees, and I don't know whether whether I will justify with my talk with the title or not. But I will try because it's before going to start, I want to say this. So this action on trees actually it's a very general topic you can say in mathematics because in this subject in this not subject in this era this the graph theory, the topology, group theory, all we will do all together, you can see. So I don't know whether I will give you much example or much proof of the theorems, but I will try to give you some glimpse so that you can after the talk you can motivate somehow I will try to motivate you, yeah. So that you can try this subject on your own. So let's start. So first so how many of you know about these group actions? uh, have you studied? If can someone tell me whether they are comfortable with the group action or I will recall it. Hello.
Recall it, sir.
Okay. So please feel free to ask any question because I know I will make mistake, and so please stop me and if I have I'll go wrong. So group action. So it's a very important tool to in group theory actually. So if I have a group G and X be any object, so this object can be said that can be group and that even that can be a space, topological space, or a metric space. It can be anything. So that's why I denote it by object. And G is act on X. G will acting on X. That will imply that there is a homomorphism phi from G to this automorphism group of X. And in some books, you will see this automorphism group is not there. It will say it is a symmetric group. So I am using these two symmetric group and automorphism group. Both are same because in the graph base this will not differ. So now, in other words, you can see this when G act on an object X. This is nothing but this. There is a map G cross X to X, and where this you can say that G and X will goes to some G dot X, and this dot is a defining relation. That this is the defining action relation, you can say. And with this, with the property that this identity will stabilize your X. That is, it will that if you act identity on X, then it will not it will stabilize. It will not go in somewhere else in the X, right? And this is the associative property. That is, if so it is the associative property. So this G dot X, G dot H dot X will G dot H dot X for all G, and this is for all X actually. So this is actually whether these definitions come about the group actions. That this is the the definition of the group action. But you can actually see that this group action will involve this representation. So you can say what is the relevant that this phi and with this definition. This is a definition. This is also a definition. So what is the equivalence that? Because it is equivalent because if you have this group action, let's say this group is act on X. So this G cross X to X, you have an operation that let's say Gx goes to Gx, right? And and now you can fix this G, right? Now if you fix this G, let's say if you fix this G, then you can define a map from phi G from X to X, right? So where this phi G of X is nothing but G dot X, this same. And you will see that this phi G, that is X to X, it will nothing but a bijection from X to X. You can verify this, and this so you can say this phi G belongs to the symmetric group of X. And we know that this automorphism is nothing but a subgroup of the symmetric group of X, right? So you can say more here. So that's why this definition through homomorphism came, and this is also homomorphism because of this relation. This is also a homomorphism. So I will yeah. So see this phi G. What I was saying that this G goes to this phi G. So I can now say that G to symmetric group of X, and this is a map phi is from G to symmetric group of X, and this phi G is nothing but phi suffix G. What is this phi suffix G? Phi suffix G is nothing but this map, right? For every G. Now this phi suffix G belongs to S to X because phi suffix G is from X to X. This belongs to the symmetric group of X, and this phi GH of X is nothing but, you can say this is this one. Phi GH of X, you can say this is GH dot X, and you know that this is nothing but G dot H dot X by this associativity property of this what I was saying about earlier definition. So this is nothing but we are hitting G on HX, right? We are hitting G on this HX. So that is this phi G of HX, and this is nothing but we are hitting phi G compose phi H on X. So from this I can say this is nothing but a family of automorphism from phi FG, where this is holds, right? So is the definition clear? Because this definition says because in the group action the definition is important, nothing else. If you understand the definition well, you will understand the group action very well actually. So is the definition clear?
Yes.
Okay. So since there are BSc and also the 12 the students for class 2, so I think this session should be more interactive because I don't have so much material. So okay, so please try to cooperate with me. So now there is a thing about the orbit. You all know about these orbits in our solar system. This is nothing but same actually. So if you have an element, let's say x in x, so let x in x, this is an element, right? Now you, and this is G, let's say this is a group G, and you are picking an element G from G and try to hit this. So this element will go to some Gx, and again if you want to hit it with another one H, let's say, so this will go to some HGx, and if you want to hit it with the cyclic group generated by G, so this will go to some X, goes to some Gx, and then it is goes to some G square X, and this will goes to some G cube X, and this will go until let's say it's a cyclic group of order n, that is this is isomorphic to some Zn. So this is some G to the power n minus 1x, and this will give me a cycle, right? So because G to the power nx is again x, because it's identity. So this is the orbit of this x. So this definition is, I think this is clear, that this orbit of some element x is nothing but this whether this x will travel through the G. So that will I think justify with the definition justify with the name. So now the stabilizer is nothing but the elements of G which will stabilize this x, the elements of G which will stabilize this x, and that is it will so all those G such that this x is stabilized for every x. This is the stabilizer, and you can see this is a subgroup, and this is the famous orbit stabilizer lemma, that that the cardinality of this orbit is nothing but the index G with the stabilizer. And now I want to define another definition, that is a free action. If the stabilizer is identity, then then you can say this is this action is free actually. And now actually you can see the stabilizer in another form. I want to put it here. So that is let's say you know that if you have an action G on X, that imply you have a permutation representation phi from which is a homomorphism from G to some symmetric group of X, right? Now if you have X is nothing but, let's say X is can anyone say that if X is 1 to n, then what is this permutation representation? G will be phi will be from G to where? Can anyone say?
Sn.
Yeah. So it will go to Sn, right? So this is a homomorphism. So since this is a homomorphism, it is evident to see the kernel of this homomorphism. So this kernel of this homomorphism is nothing but all those G in G, and you know that homomorphism how is defined. This G goes to phi G, and this G belongs to G such that this phi G is the identity map. And this is not identity, this is the identity map on X to X. That is, you can say this G belongs to Z such that this phi G of X is equal to X, right? So this is actually G belongs to G such that G dot X is equal to X. So can you okay, so forgetting. So now I will so these are some examples of these group actions. That is, the first evident example is there's nothing but the identity map. This is a trivial action, and the second is one I already explained you, that this is nothing but the bijection, where the image is nothing but the symmetric group. And I want to tell you some more it's more important definition. These are very more important examples, and these are very general example, but very useful. So first one is this, that if you have a circle S1, so you know this circle is represented by all those Z in C such that this modulo Z is 1. And if you fix some real number alpha, let's fix some real number, and you can see this Z actually act on S1 by rotation, right? How? So let's say n and z goes to this e to the power 2 pi I alpha n, where this alpha is fixed, z. So you see that this is a rotation. How? So let's say you put a z belongs to S1. So you just pick a z belongs to S1. So this z has, you know, this is belongs to S1, so it will look like some e to the power 2 pi I theta, right? Now what can you say about this? This is nothing but e to the power 2 pi I theta plus alpha n, right? So you can see this will rotate your z. So this is, let's say, z prime. So this z prime is nothing but you will rotate to alpha n angle, right? Now can you say, so let's say alpha is belongs to q. Let's say alpha is belongs to q. So what can you say about the action? So let's say alpha is belongs to q. Let's say alpha is nothing but p by q, right? So I am fixing it. So my nz goes to e to the power 2 pi I alpha, e to the power 2 pi alpha, 2 pi p by qn, right? P by qn, right? Now if I choose n to be q, I can choose n to be q. So this q is z goes to e to the power 2 pi I, and this is q, so 2 pi I p, right? Oh, I think I have made some mistake. This times z. So this times z. So what is the position of this element in circle? Can anyone say? And this p is an integer, right? Can anyone say what is the position of this circle? Position of this point, new point z prime in the circle?
Z cos something cos 2 pi p.
Yes, but don't go into this cos theta sin theta. Just see the geometry, nothing else. This is the beauty of this action. The action nothing but defines the geometry of your object, whether you are acting on it. So what is this? This is, can anyone say? Because this, what is this? So this is nothing but this will not change the position of j. It will again rotate and then it will come to this jet. So it will stabilize the jet, right? It will stabilize the element. So is this clear? So this portion, I don't know whether so so this z prime is nothing but this, the position of z and z prime is same, but let's say this is z and this is 2 pi I p, and this p is an integer. So it will nothing but it is 1, nothing but actually. Hello, it is 1, nothing but. So it will actually trace the same point here. So if alpha is belongs to q, you can always see that there exists a g in my z that will stabilize every element in S1, so this is the question. Actually, this is an exercise, and it's a very easy exercise. If alpha is belongs to some irrational number, you will see that no element of z will stabilize this element in S1. You can see that if alpha is belongs to irrational. Okay, so I will go into the next example. So I think everybody knows this group, this GL2R, that is the all matrix 2 cross 2 real matrices which has determinant non-zero. But I am here using another group, another group, that is GL2R plus. That is nothing but positive determinant, nothing else. That's why plus. So I will execute an action of Gl2R plus on this H2. What is H2? H2 is nothing but your upper half plane. Your upper half plane, right? So that is all those Z, that is Z is nothing but x plus iy, and where y is positive. And you can also, if you can see, you can, oh, shit, if my pen has freeze, sorry. Hello? Yeah, am I audible? I think I have some issues on
Yes, it's okay.
Okay. So you can see this nothing but all those Z such that this imaginary part of Z is positive, right? So this is the upper half plane, and so this is, you can say, this upper half plane. So this Gl2R, I will see this. I'll explain this example. So this Gl2R will act on your this upper half plane. So what is the action? So you can take any element in Gl2R, and you can act on some element Z in your upper half plane. And I am defining this action that Az plus B by Cz plus D. If you have seen some complex analysis, you can actually familiar with this action, and this is called nothing but fractional linear transformation or some Mobius transformation. But if you have not seen this, it's okay, but just try to see here first time. So let's say A, B, C, D is acting on some Z and give me some Az plus B by Cz plus D. Now can we say that this is, so this is action, so this is a map from Gl2R plus cross H2 to H2, right? So this should be in H2, right? This should be in H2. So that is, imaginary part of this should be always positive. Now if you, so this is imaginary part of this, so you can see by calculation, and this is a very easy calculation, plus two things. So this is nothing but AD minus BC times imaginary part of Z by mod of Cz plus D whole square. And this is positive, and this is positive because I am taking my element in Gl2R plus, that is positive determinant, and this imaginary part is also positive, imaginary part of Z, because I am acting on some element Z which is already in H2. So you can see this is in H2. Now just observe these things so okay, fine. So I have a question, that is, can you tell this this is a group, right? Gl2R. So what is the center of this Gl2R? Can you say? Anyone? Can anyone say what is the center of Gl2R? So now see, these are very interesting facts, because I am you can see these are more geometric, not algebraic. You can see this upper half plane, I am acting an element of upper half plane. So I think this should be more interesting. Jay, so can you see this? Can you tell me what is this center of this group Gl2R? So it's a basic question, I think. So can anyone? Okay, if you so this basic group theory will tell you these are nothing but the scalar matrices, lambda I2, and lambda is belongs to R minus G. Okay, so you will observe that, okay, let's say this is R plus, so you will observe that this scalar matrix, so let's say A, B, C, D. So let's take a scalar matrix as lambda 0 0 lambda. Okay, so this is a lambda scalar matrix. So this will nothing but Az plus B by Cz plus D. So this is lambda Z by lambda Z plus D. So yeah, so lambda Z by lambda Z plus 0 times Z plus lambda. So this is lambda Z by lambda, and lambda is non-zero. This is Z. So you can see this actually acts trivially on H2, right? This acts trivially on this upper half plane. So we can make my action more stronger, that instead of this Gl2 plus R, I can act Sl2R, that is the special linear group, on this H2. Same. So here nothing but I will take this determinant should be 1. So this will again positive. So this is an well-defined action, you can see, and then this Z of Sl2R will be nothing but this plus minus identity, because this lambda should be mod lambda is 1, but mod lambda, since we are in real number, so this lambda should be plus minus I. So this is plus minus I. So if we moded out this thing, so we'll see this PSL2R a new group where this SL2R modded out by this. So you can see this if we act this will not act trivially. This will be a faithful action, and this is a transitive action. So actually I am modded out the problem, right? So I am modded out this plus minus I, because plus minus I, if I act SL2R on H2, then this action the trivially act element will be nothing but plus minus identity. Now since I will model out this plus minus identity, so SL2R by the Z of SL2R, that is the center. So this will any element of PSL2R will not act freely, right? And moreover, it will be faithful action. Okay, it will be faithful action, and this is a transitive action, that is, it has only one orbit. You can see this. So these are some basic exercises I want to tell. Very interesting exercises. But what is this group? Tell me. If you have if in some geometry courses in future, you will see that there will be a metric which will be induced in this H2 upper half plane. So this is called the Poincare metric. And this, with respect to this metric, if we collect all the distance preserving maps, which are called the isometric group, and this isometric group of this H2, I know that this is not evident here, but I'm just trying to tell you that isometric group of H2 will give you this PSL2R. Okay, so you will see that there is some metric which is called some Poincare metric, which is acting on this H2. With respect to that metric, this H2 is a metric space, and this if you collect all the isometry, that is the distance preserving map from H2 to H2, so this group will give me some PSL2R things. So from this you can say that if you take any metric space X, D, so you have this is useful to see the isometric group of that X which is acting on that X. So this is an example. You can say this is a very important example, that you can act you can take any metric space and take the isometric group and act it on that metric space X by this by like this GL2, ASL2R, or PSL2R. So this will actually give you the geometry of that X. It will give you some geometry on X, but the action should be some restricted action. I will not go there. So now for the second thing, I want to tell you some groups and its representation. So you have group, like let's say you see this group Zn. What is this Zn? Zn is nothing but let X and X to the power n is identity, right? Or anything that so this is nothing but the generator which generates this Zn, we know that, and this is what? So this is the relation, right? So relation is that some element of this generating set X will follow some relation, that is will equal to some identity. So this will define a group, and this is in general. If you take any group, then this group has a generating set and a relating set, and these relations are made on the generators. So I will tell you this, and before that I want to see you the construction of some free group. Okay, so take X be any group, right? X be any set of words. Let's say X is AB. Let's say X is A first of all. Not A is not that good. Let's say X is AB. Now a word is nothing but like this. x1, x2, xn. This need not be distinct. You can take repeated words like so a, this is a word. A b, this is a word. A b a, this is a word. So you see that this is infinite. So I can make infinitely many words with these two letters, right? Now take this x inverse. So I am taking this. I am pronouncing this as x inverse, but it is not x inverse. I am defining some sets. So that is x inverse such that x belongs to x. So you may ask that if x is a set, so how can I define this x inverse? So take this x inverse as a symbol, just symbol. So what is the property? The property is that x inverse or x inverse x is defined to be some empty word 1, right? So it is defined. I am defining something, and this symbol is defining with the empty word 1, right? Now you can so from x you can this x inverse. This is nothing but some a inverse b inverse. Just take it as a symbol, and you can actually construct many words like this a inverse b, and a b b inverse. This is, or like say b inverse b a b, whatever you want to. So that is the collection is this. This is a very big collection. You know that this is a very big collection. So it's an uncountable collection, you can say. So this is the set of all words in this x union x inverse. So if you take any word, so this will look like this x1 to the power epsilon 1, x2 to the power epsilon 2 up to xn to the power epsilon n, where these epsilon i's are nothing but plus minus 1. So because I can take this x1 inverse or x, right? So this is nothing but 1. And now I will define a binary relation on this set, the set of all words. And what is the relation? This is nothing but not binary relation, binary operation. I'm very sorry. So I will define a binary operation to this word, any two words. Let's say take w and u, and I will concatenate them. That is, I will just put them together, and this will again a word. But you will see one thing. So let's say I have a word a b inverse a. Now you know that this b inverse is nothing but the empty word 1. So this is nothing but this. I can reduce this to this word. So in my group, I want to take my element such that this has the element has unique representation. And so for the uniqueness, I will define an equivalence relation, which is called the reduced equivalence relation of the reduced word on the set of all words. So what is the reduced word? So I will take this and this together and make it in an equivalence class, right? So whether I have in my word some, let's say this word, so this is nothing but a b a. So I will take these two in one class, and we will see this will give you an equivalence relation, and that is two words is related. That implies they have same reduced word, right? They have same reduced word like this. So reduced, you understand that's what I am trying to say by reducing. So this is the class of all reduced word. So I will define this equivalence relation that define the operation, again binary operation, that if I have this class, reduced word class, and this class, and I will just concatenate the word and then take their reduced class. So you will see this is this relation is a binary relation, binary operation, and together with this will form a group, and it will the group properties are hold. So group properties hold here. So this with respect to this binary operation, so this group is called the free group, and this x is called the generator. So this is called the free group on generates x, which generate x. If I take this a and b, so automatically I will consider a inverse b inverse, and this is if ab is nothing but this is called the free group with two generator, and this is sometimes called f2, right? Okay. Okay, So this free group can be seen uh, as a universal property, that if you have a set X, let's take any set X and take any group G and take any map F. So if you take any map F from X to G, then I can extend that map F to some phi, which is a unique homomorphism from the free group generated by that X to G. That is, if you have X to G be a map, X to G be a map, any map F, and X to Fx, which type? Okay. So X to Fx, so this I can say this is the identity map. So I can, because this is nothing but X is in Fx always. This is the inclusion map. So I can actually have a unique homomorphism phi such that this diagram commutes. So I can see free group as also this universal property. So these are some exercise you can see actually. That is, if you have any two free groups or any other generators. Generally, I will take my generators are finite, because this is the most useful case when the generator is finite. But if the generator is infinite, there are something we can say, but I don't think I am an expert on that. So this, let's F1 of X1 and F2 of X2, let's say this is a two free group on generator X1 and X2, and these two are isomorphic. So that will, if and only, will give you that the cardinality of X1 and the cardinality of X2 are same, because we see here this free group is nothing but depend on the number of generators. This is not depend on what is here is A or B or some cow and say goat. This is, if you say X is nothing but cow and some cat. Okay, so this free group generated on this cow and cat is nothing but this free group on two generator. So this will say this will not depend on what are the elements. What are the elements on X1 and X2? It is only depend on the cardinality. So if you take any group, then this is another very good proposition, I can say. This is a very good exercise or proposition. So if you take any group, so this group can be isomorphic to quotient of some free group, right? So if you take any group, so this group can be isomorphic to some kernel cases. So this is nothing but free group, quotient of some free group. So you can see this from this property, right? This universal property, what I have said, that if you take any X and in any G and take any map, then you can extend it to a homomorphism from Fx to G, right? Now if you take because G is a group, so if you take G to be the general, okay, so take G be any group, and you know that the group itself generate itself. So you can take this group itself, so it will always generate G. Now this G to G is an identity map, because my X is here G, nothing but. So I can actually, by universal property, I can actually extend to a unique homomorphism phi from Fg to G, right? And this is a homomorphism. This is a unique homomorphism, and you can see this is a onto homomorphism. So it is evident that you can see the kernel. So Fg by kernel phi is nothing but isomorphic to Z. So you can see that any group can be thought of some quotient of some free group, right? So this is no more exercise. Okay. So this, what is this car phi? This car phi is nothing but all those element in Fx, that is Fg or Fx, anything. So element, so W, so W, here I have written. So W belongs to car phi, that implies this phi W is nothing but 1. This is nothing but identity of G. And if W is some x1 to the power, because it's a odd and free group, so it's nothing but some x1 to the power epsilon up to 1 to up to xk to the power epsilon k. So this phi of xi is, let's say this is ai, because you see that, you know that the if you have a homomorphism, it will send the generator to the generators. Now if I take this at the generator of my phi group, so it will send xi, if xk is sent to some ak, so this ak is nothing but belongs to the generator of my group. You know that this is a very basic group theory idea, that is generator sends to generators. So this is also a generator of G, right? So this phi w is nothing but, by homomorphism property, this is nothing but a1 to the power epsilon up to ak to the power epsilon k, and this is 1. So this is nothing but belongs to G, because these all are, this is an element, let's say this element is G, and this G is belongs to G, and this, so this is define you the relation. So this defines some relation on your group G. And if you take some generating set on this kernel, that is the set of all relations, so you will see that any group can be represented by this generator and with this relation. So like you can say this Zn, right? So you will see that you have a homomorphism from from fx to Zn, where this x is nothing but generates this Zn. Okay, and this I am taking the free group on this x, and x goes to x to the power n. So this is a homomorphism, and here this we know that this x to the power n is identity. So this is the kernel is nothing but this. So you can see this Zn is nothing but this x free group generated by x by xn, right? So this will nothing but this this collection, all those x as that x to the power n. So this is the representation, right, from Zn. So you can see group by this. Actually, group are seen by this. So now I will go to the main topic maybe. So this is the group action on a graph. So we from now we have said this x is nothing but an object, a metric space, anything I can see. So this group now we will see what do we mean by group action on a graph. Now we know that this graph is nothing but a graph x is nothing but consists of subset of vertices. I am writing this notation x naught and set of all edges x1, right? And we have these two maps. Okay, actually three maps. I will define something. So we have these two maps alpha and omega, which are from x1 to x0. So this alpha is nothing but you. So this is x1. Let's say h, and this is nothing but your initial edge, and this is nothing but your final edge. And another thing you can say, this bar is from again x1 to x1. So nothing but you can say phi here. So phi is nothing but e bar. So this is, if you have this trace, this directed graph. So by applying this map, you are telling this one. So these are three maps I can say. So and tree is nothing but a connected acyclic graph. That is a connected graph which contains no cycle. So now I will define what do we mean by action on action of a group on a graph X. So I'll define something left action, anything you can say. So now so X X be a group and X act on some X, and X is a graph. X is a graph without inversion of edges. So what is this imply without inversion of edges? That is, there doesn't exist any G in G such that G dot E is equal to E bar, right? Because E is an element of X, right? E is an edge. So when I will apply G, so it will not backtrack that edge. So that is nothing but inversion of edges. But I will say here, I am not saying more about this inversion of edges, but I can say if I drop this notion that drop this restriction without inversion of edges, still we can do action on graph by defining some bicentric subdivision. But I will not say this here because it's an algebraic topology thing. So let's start with with this thing without inversion of edges. So this is a pair of actions that G. So let's say this is a E, and after this action on G, this will go to some GE. Okay, so this is an H. So if you take the alpha, this is the alpha of G, that is the initial vertex, and this is nothing but this is alpha E. So this G of alpha E, that is when I will act on this vertex, so this will go here, that is alpha of G, right? So this is the nothing but definition. and you will see that this is evident, right? If I have a initial vertex of some edge, when I may apply some g, so it will act orbit is nothing but this nothing but g. Now you can see, you can actually define some factor graph or some quotient graph out of this action. We know that after this action we have always defined this orbit and stabilizer. So here same I will define some notions on these orbits, that is on the quotient graph. So factor graph or quotient graph after action, if g act on some graph x, so the quotient graph is nothing but a graph with vertex your orbit and edge your orbit. So in the graph I have the vertex, my vertex is v and edge is, let's say, e. So in my graph I have this e and here is v1 and v2. So after action in the factor graph, this should be orbit of v1, this is nothing but orbit of v2, and this is nothing but edge should be orbit of the edge e. So this is what this factor graph came, right? So you can see this example. If you see this example, we will applying 1, we will get e1. After applying g, I will get g of e1 is nothing but e2. After applying g square, I will get g square of e1 is e3. After applying g cube, what is this? So this is g of e2 is e3. That implies g of e1 is e3. So that implies g square of e1 is e3, right? And from this I can say, this is nothing but g cube of e3 is e4, and this is e1. So the orbit of e1 is nothing but all the elements of e1, all the elements of the this is nothing but this set edges set, right? And what about the orbit of some vertex v1? So you will see that this e1 goes to e2, so v1 goes to v2, right? So this is nothing but v1 v2, and again e2 goes to e3, so v2 should be goes to v3, and e3 goes to e4, so v3 should be goes to v4. So this is nothing but so you see that this is a transitive action, and because this orbit is nothing but the whole set, and the orbit of the vertex is nothing but the whole vertex set. So what is this? So what is the factor graph? This factor graph is nothing but only one. You have only one vertex, because the orbit consists every vertex. So this is only one vertex and only one edge. So this is a loop. So the factor graph of this is nothing but a loop. So this is the group action on the definition of a group acting on a graph. So when a group G is act on some graph X, and since my title of this talk is group acting on some tree. Okay, Apurva, how much time I have? Hello.
Hello.
Yeah. So how much time I have?
Bhaiya, we told to 1 hour, no?
Okay.
Because
okay.
we are having another session. You have 10 minutes. 10 minutes.
Okay, so I will get 10 minutes, right? Extra.
Yes.
Okay. Thank you. Okay, so see, if you have a group G which is acting on some X, and since the title of my talk is action on a tree, so it is evident that I will take X is a tree. But you will see if you go through these things, so this is the starting point of many things, that is combinatorial group theory, geometric group theory, hyperbolic geometry, anything. So you will see this X is a special tree. This special tree, X is a special graph, I can say. So this graph is nothing but the Cayley graph. So in this courses, that is on the combinatorial group theory or this hyperbolic geometry, everywhere this action is G act on some Cayley graph. So G act on some Cayley graph. So I will now define this Cayley graph, that G be any group and S be any set. So the Cayley graph is a graph, first of all. So it should be a vertex set and a edge set, right? So So calligraph is a graph with the vertex set G. That is the okay. So talk about G is finite. Okay, whenever whenever G is infinite, I will tell you. So the vertex set. So for now, I am just expecting these finite groups G, but it is not evident that G has to be finite. It can be infinite graph. So, so with the vertex set G, and for every G and for every S in S, what is this S? S is any set, right? So, for every G and for every S, there exists a edge between G and GS. Okay. So you take an element G in G, and you take an element S in S. So there exists an edge which is from G to GS, whose terminal vertex is GS and the initial vertex is G. So that is the Cayley graph, you will see. Now, so I am searching about group which act on some tree. So my question is when this Cayley graph is a tree, and this is a very interesting answer. So for tree, it should be first connected and acyclic, and it is an interesting thing that this Cayley graph is Cayley graph is connected first of all, because for tree it is a acyclic connected graph. So for the connected, the S is not to be any set. S should generate G, right? So to see the Cayley graph, so to ensure that your Cayley graph is connected, this set that is G S should generate G. That is, S is a generating set. So if you take any G, it belongs to G. So this G can be written as some S1 to the power epsilon 1, S2 to the power epsilon 2, up to some SR to the power epsilon r, where this epsilon r belongs to plus minus 1, because I am taking inverse and this thing, and this SIR belongs to S, right? Because S generates this. And now you can take S1 itself. Okay, so you will see that S1 belongs to again G, because it generates G, so it should be in G. So you will see that there exists a edge from E to S1, right? So E to S1 to the power epsilon 1, you can say. S1 to the power epsilon 1 to S2 to the power epsilon 2. S1, S2 to the power epsilon 2, right? By definition of the Cayley graph, because you have an edge from G to GS. So if I take identity my first element, then I take S1 to the power epsilon 1. Then I can take S1 epsilon 1 S2 to the power epsilon 2. This epsilon 1 and epsilon 2 are plus minus 1. That is inverse and all that. Then I have S1 to the power epsilon 1, S2 to the power epsilon 2, S3 to the power epsilon 3. So I have this edge, right? Always this goes to up to, you can say, G, which is nothing but S1 to the power epsilon 1 up to SR to the power epsilon 1. So in that case, you will find this should be connected. Actually, this is a very easy exercise. And another thing is that when your Cayley graph is a tree, if and only if this G is a free group. Okay, your Cayley graph will be tree if and so this is the you see that this graph theory, this tree is actually connected with this group theory, right? So this Cayley graph is a tree when this group is nothing but a free group on generator S, right? Now this is also exercise, but I have proved actually this Cayley graph thing. So you can actually see this in any textbook, but since I haven't much time, I will skip this proof and I will go to the next one. Okay. So from this, we have seen that this Cayley graph is a tree if and only if your G is free. The vertex set should be free group. So this is another main result, that if you have an action G on X, a tree, and this action is free action, that is the state. Whenever you have this GV is V for all V, this G should be identity. So this stabilizer should be identity. Whenever this is a free action, then if a group acts on a tree freely, then the group has to be free. Okay, so this is the main result. I will not prove it because it is a big theorem. So if you try to just see the beauty that whenever you act you take a group, you act on a tree and see this action is free, so you will see that this G has to be free, right? And from this a direct corollary is the Nelson-Shape theorem, which says that subgroup of a free group is free, because it's a direct corollary that if your group act on if you take a free group, then is by this implication, this free, since G is a free group, so G will act on a tree freely. And what is your tree? You will see that in the proof that this tree should be some Kelly graph, where this Kelly graph of some Kelly graph, because G is a free, so you can say that G is let's say G is free, and you can see that G is act on some G Kelly graph of G on S, right? So this is a free, this is a tree, right? Because G is free by the previous statement, so you can say that this is a free action also. So one arrow is one way is very evident proof, but other way you have to do something with the lifting property. But I will leave that. So if you have a subgroup of a free group, so the subgroup also will act free, right? If you have a group, this acts free, because so the identity is the only stabilizer. So for the subgroup it will also same. So the subgroup also act freely, right? So that implies the subgroup is also free. So subgroup of a free group is free. So now I will define something, the notion, the fundamental group in 5 minutes, the fundamental group of a graph. If you have some algebra topology knowledge, you will see that this, not algebra topology, if you have a topology knowledge, so you will see that these two are same actually. But if you haven't, it's no problem, because I am defining it right now. So if you have a graph, let's say G be a graph. If I have a some graph, right, it will something like this. So if you have a graph, so take any vertex X, and now you will consider all the path, directed, undirected, whatever it is, all the path which start from X and end in X. So these are loops, right? So all the paths, not curves, all the paths which start from X and ends in X. And so this is the P, right? Now we will see that. So let's take this picture, this graph. So X, E1, E2, E3, E4, E5. So I will take this E1, E2, E1, E2, then E2 bar, that is I will again, so E1, E2, then I will again come back here, then E3, E4, E5. So this is a path, but here I have used this. So this is my thing. So I will reduce it to the E1, E3, E4, E5. So you will see that E1, E3, E4, E5 is again a path. So I will define equivalence relation on all the paths, right? All the paths. So the relation is like that. So whenever there is a backtrack here, this EI types EI bar, so I will drop it. So and take this as equivalence classes. And if I take any two paths, I will concatenate them. So this will again a path. And I will define this concatenation like the free group, this binary operation. And under this binary operation, you will see that this will be a group. And the group is called the fundamental group of the graph. Okay. So can anyone say that what is the fundamental group of a tree? Can anybody? What is the fundamental group of a tree? So you have a tree, right? You have a tree like this. So tree is nothing but connect this type of things or this. Let's say this. So can you say what is the fundamental? Can you say fundamental group of a tree? Can anyone? So you can see that if I start any vertex and take anything, so let's say take a map. So let's say very simply, yeah. So take any map. Take any path. So this will always collapse to this point, right? Because if you take any here x and a path, let's say this is a path from x to x, but you will see that I am using this is twice. One is going up and one is going down, and another is going right and another is going left. So it will collapse by the equivalence relation. So every tree will be collapsed to a point, you can see. And so the fundamental group, this point is nothing but the identity. So fundamental group of a tree is nothing but identity, right? So it's a simple. And this fundamental group doesn't depend, it's like same thing in the topology. The fundamental group of a tree, of a graph doesn't depend on the vertex, whichever vertex you are choosing. Okay. So for the fundamental group, I want to just say one thing, that the new group construction, that is the free product of two groups. If you have two free groups, you know that free groups has no relations, right? Because free groups is a free, that's why there is no relation on this. Free group is generated by this, so you can say that the relation set is phi. Free group has no relation. So the free product is nothing but this. We will consider the union of the generators, and again this. So another example I can say, let's say Z. So Z is a free group, right? So what are the generators? It's only one generators, right? With no relation, right? There doesn't exist any n, which is an is identity. So Z is a free group. So you can say this is A with some phi relation, and then take another Z. Let's say another some generator, which is, let's say, representation is this. So what can you say about the free product of Z cross Z? This is the free product side. So from this we can say this is A comma B, and it's a free group. So this is nothing but free group on two generators, F2, right? So there is another product. So this is a free product, but if I want to relax, if I want to not relax, if I want to restrict some condition, that is an amalgamation product. That if you have a group, let's say G1 and G2 be two groups, and A be another group, and you have a injective homomorphism from A to G1 and A to Z2, so you can construct a new group here, where so G1 has a representation like X1 with R1, and G2 has another representation with X2 with R2. So this G1 star G2 with amalgamation A will be always X1, X2 and R1, R2. This is true because the free product. And when this is amalgamation, so I am imposing the image of, this is a 1, so I am imposing the image of, is embedding. So I am image of A here and A here. So I am imposing gluing the image of A here. So this is nothing but L1A and L2A. So I am imposing these two images. So one example I can say that I will not say any example. I will say later. So one thing is one example of this amalgamation is say about this Van Campaign theorem. So this is not a this is a topological version, but if I want to restrict myself in the graph theoretic version, so this Van Campaign theorem is nothing but if you have a graph X, and this X is a union of U1 and U2, where this U1 and U2 are the path connected space. You know that any tree is path connected. So U1 U2 are path connected space, and U1 intersection U2 is also path connected. Then this pi 1 of this graph is nothing but this pi 1 of U1 and pi 1 of U2 and amalgam with the pi 1 of U1 intersection U2, right? So like this graph, let's say this is the example I want. So yeah, take this graph. So this is a graph. Let's say this is X, right? And you see that this is U1. I am taking. So this is the 3 blocks. You see that this is a 3 block cycle graph, and so the first block is actually has only one generator, the fundamental group, that is 1, that is A. Because if you take any vertex and you will see the cycle, so it has only one generating element, so that is A. For the second block it has same B, and for the third block C. Now we will take U1 to be the first two blocks and U2 to the second two blocks, last two blocks. So this U1 union U2 is X, and this is path connected, and U1 intersection U2 is nothing but this block, right? Now if you want to apply this Van Campaign theorem, this pi 1 of X is nothing but this pi 1 of U1. So what is this U1? This will be the pre product on A and B. Yes, because it is generator A and it is generator B. So this is pre product on 2 generator F2, and for the second one it is also pre product on generator 2 B and C, but the amalgamation is intersection. So intersection is nothing but this. So this is nothing but only generating C. So the pi 1 of X is F2 star F2 amalgamation is Z, right? So this is the thing actually. So you can actually relate this to this if you know something, if anyone for the M.Sc student know about these genus 2 surfaces, you will see this genus 2 is nothing but this gluing these two torus with torus without with the discs removed, and gluing amalgam. This is Z pre-product Z pre-product Z. So this is the rod pedal, and this is the figure 8, which is this is look like 8, so that is figure 8. So this is waves of two cycles, so it's F2, right? So you can see that if I have a rose petal with n petals, so this pi 1 is nothing but Fn by this theorem, this pre-product, that is Z, this pre-product Z pre-product Z. So you can see one thing. So take a graph, any graph, you can see. I think I have written some graph. Okay, yeah. So take a graph. So this is a graph. So you will see that these two can collapse in a point, right? These two can collapse in a point. So these two can collapse because it's a real line, right? It's a line, so it can collapse. So this can be collapsed. So this whole graph will be equivalent to this cycle and this cycle, and they will be concatenated here, right? So all the graphs can be equivalent to some roach petals for some n. If you take any graph, so you will see that any connected graph, obviously. So this connected graph will be equivalent to, what is the equivalence? Equivalence is that same equivalence when I introduce a fundamental group. That equivalence, because this line has to be contracted. This can be collapsed to a point, right? So only the circle for a graph, connected graph, the cycles will left out, the loops will left out. So pi 1 of any connected graph is actually Fn, and this is some n. This n has nothing to do with any number of vertex or number of edges, nothing. This Fn is some n. So pi 1 of any graph is free. That is the thing, right? So pi 1 of any graph is free. So this is the main, this is the very nice statement, that if you take any connected graph and if you take the fundamental group, this has to be free. Now, what is this n? What is this n? So this is the interesting, that this n is nothing but e minus v plus 1. Okay, so e minus
Hello,
yeah,
sir.
yeah, one minute. So this n is nothing but e minus v plus 1. So you will relate this to the Euler characteristic of some graph. So this is nothing but f to the power minus Euler characteristic of some graph. Okay, fine. Let's forget about the Euler characteristic. But this is very interesting, that pi 1 of some connected graph is free, and the n is nothing but number of edges minus number of vertices plus 1. So yeah, so this is all. Actually, I have something to say. Okay, but the time is running out. Okay.
Thank you, sir. Thank you so much. Actually, sir, we are having another session at 3 p.m.
Okay, no problem. No
And-
problem. Actually I start very slowly.
Yeah,
It's
no, that's not matter, sir. Actually, and we need some time, at least half an hour, to prepare our
Yeah.
next session. And
Okay.
one more thing, the everyday 3 session, that is become some headache for us also.
Okay,
So
okay,
we
okay.
have
I'm
done it.
sorry to take this. Okay.
No, sir, no. Don't say sorry about that. So, thank you. We should say thank you that you have accepted our invite and you have given over the beautiful lecture, explained so many things about graphs and teeth. We have also got to know so many things. So it was a
Yeah.
wonderful session.
Some participant also
So
has messaged me to, if possible, you may share the materials, means
Yeah,
PDF. If
I will share the material.
hello,
But
sir.
yeah.
One more request. Can you please open your camera for 1 to 2
Yes,
minutes so that we
yes,
can take
yes,
some
yes,
snaps for our social media platform?
yes.
Suparna, do that. Hello,
Okay.
Suparna.
Okay, Dada.
If possible, everyone, please keep your camera on.
okay, thank you.
Okay.
Thank you,
So,
Sagnik.
Thank you, sir.
so is there any
Thank
Thank you
you so
so
question?
much.
much, sir.
Okay.
Ah,
Thank you
okay.
so much.
Okay. Thank you.
Okay.